All right, let's get going. Thank you everyone for joining Basemark webinar today. So my name is Sami Niskaan, I'm CEO of Basemark, and with me I have Damian Nutzman, who's the technical artist and the project manager for PATS product, and Damian will be the star of today's presentation. So the topic of today is benefits of Basemark Automotive Test Suite for Automotive HMI development teams. Before I let Damian loose, a little bit about Basemark as a company and our offering. So we are a software company based in Finland who's offering tools for the companies who develop the next generation autonomous and connected vehicles. Our products range from runtime engines and middleware to SoC evaluation and testing solutions. We also have a professional services team who's supporting customers in the field of the autonomous drive as well as in HMI development projects. Basemark is Automotive Grade, so we have a long experience in embedded and mission-critical applications. Our expertise are in benchmarking, graphics, as well as compute solutions. We have partnered successfully with world's leading automotive OEMs, Tier 1 companies, as well as semiconductor companies in Europe and US, and developing autonomous drive in-cockpit AR applications, instrument clusters, and IVIs. So Basemark's strength is whenever there is a need for small footprint, guaranteed uptime, and long-term support. We have basic ISO certifications, and our offices are TISAX 3 certified. For our software products, we are currently working on enabling functional safety certifiable products, ISO 26262 certifications. And then a bit about the offering before we'll start talking about PATS as a product. So if you think about the automotive stack, we offer services side on the autonomous drive as well as the HMI development for our own graphics and compute implementations, but also using the industry standard frameworks and tools as well. Then we have rock-solid graphics and compute offering, which is basically a middleware offering to accelerate graphics and compute computations in the automotive environment. And then we have the SoC evaluation tools to evaluate the overall performance of the graphics and compute applications within the automotive SoCs. So this is the company and the products in the very nutshell. And then I'll hand over to Damian. Please go ahead.
Yes, thank you, Sami. So first of all, I'll introduce myself quickly. I'm Damian. As Sami mentioned, I'm project manager and also doing HMI development here at Basemark. And I will basically be describing BATS, what's BATS used for. I will demo BATS as well, discuss the information you can get out of BATS to both evaluate SoCs and accelerate HMI development as a result. And that's it pretty much. But before I do that, would kind of like to, a few minutes, kind of discuss the background for BATS. Where is the need for BATS coming from? At Basemark, we've been doing HMI development work with automotive clients. And often what we found happens with automotive OEMs is that often they have their concept and requirements and they try to implement them in the in-car implementation, but often they cannot reach their target frame rate, their target performance for their HMI applications. And the main reason for this, when the SoC in itself is evaluated and chosen, they're often using sort of gaming-focused benchmarks, like the benchmarks that Basemark has been creating, or other benchmarks that stress the device using some classic gaming workloads that stress utilize different rendering features than you would use in HMI or UI. There's an often misconception that UI is simpler cheaper to render than just gaming workloads, gaming environments, characters, models, and such. And this is sort of a misconception that comes from misunderstanding the requirements for rendering UI and the complexities of it. So they're stressing the devices with workloads that are not realistic to what they would actually implement in the car. And when they actually implement, so spend some time creating concepts and beginning to produce them with design engineers and HMI developers, the frame rate is often undesirable. They cannot reach 60 or 30 FPS. They're running multiple applications at once, instrument cluster, IVI, doing computer vision, accelerated on the GPU as well, and they cannot reach their performance target. And what happens is they have been contacting us, as we have a lot of graphics experience, to come and help them, first of all, try and optimize their existing implementations. And often what happens is we optimize whatever we can, but sometimes we have to go back and tell them, these specific concepts you're trying to implement are not realistic for the target device. They're often running on devices like the IMX6, which is very underperforming, and their concepts are not feasible. So they have to change the concepts after production have started, rework the concept over and over again, implement it, downscope in certain cases, which is very time consuming. They basically wasted a lot of time implementing things that cannot give them the performance they want unless they change the target. So whenever we can, we try to help them optimize, but sometimes there's misalignment between concept and requirements and technical feasibility. And that's the reason for BATS. Historically, we have been making benchmarks, and we realized there's a need for a benchmark that stresses for UI and then automotive HMI workloads and parallel test orchestration with a mixture of graphics tests and computer vision tests. So the SoCs can be evaluated for what they're intended to be used for. And this is BATS. This is basically, BATS is a collection of graphics and computer vision tests with a focus on UI, HMI rendering, and computer vision. So that's BATS in a nutshell. Now I will actually go into specifics, the graphics tests and computer vision tests that are included in BATS and how they can be used. So I'll kind of move forward a little bit. But as I mentioned, BATS is a collection of graphics tests and computer vision tests that can be orchestrated, combined together and tailored to match the actual concept requirements and what you would actually run in the car. So using a tool called the Orchestrator, the user can select a myriad of tests to run in parallel, both graphics and computer vision, with OpenCL acceleration or without. And these tests I will now show you. So the user selects the tests, configures the tests, and launches them either locally or remotely via SSH on target devices, or ADB if it's using Android. Running the tests and then evaluating the results, which I will also detail a bit later. So talking about the graphics tests. The graphics tests, and this is an important topic. For these SoCs, they're actually they're ranging quite a lot in performance. From the low end to the high end, there's a huge gap. A device like the Samsung Exynos performs a lot better than something like the IMX6, and there's a lot of range in between. So to properly test the wide range of devices, you need a range of tests ranging from low end, entry level, to mid-level, to high end, and also an IVI test that usually can be run with any of those. And also we plan additional tests in the future, AR-specific tests, both video and over AR, so AR over HUD projection, and also a navigation-specific test that procedurally renders an environment using localization data. And also another important aspect of that is the fact that we're cross-platform and cross-API. We support a range of graphics APIs. So GLES, which is very, very commonly used, GLESSC, and also Vulkan, which will probably and hopefully will be adopted more and more into the future as it gives developers more control to squeeze every bit of performance that can be squeezed out of the device. And also computer vision tests. Computer vision tests accelerated with OpenCL or without acceleration on the GPU. So either testing core, test functionality, so histogram, cutting edge detector, fast corners, so on, or a video stitching test that utilizes different types of stitching that can be configured to stitch a video in real time that would often be used for example, Park Assist, visualizing the 360 Park Assist feature, and then we could project it onto a cube map or sphere map and use it as the environment for our Park Assist feature. And in the future, we'll also have additional tests like ADAS specific tests, so object detection and classification, sensor fusion, and so on. And being able to run it with and without OpenCL acceleration is also a very nice thing to evaluate how it affects performance on top of the graphics rendering. And that's it pretty much. Now we'll go into the challenges. So I mentioned that rendering UI, HMI, can have different, I won't say problems, but different challenges compared to just rendering, let's say, a 3D environment with lighting and complex character models and animations. UI has its own challenges that can often become very expensive to render if not done carefully. And sometimes it is just expensive, and this is the way it is, and you cannot do anything about it. UI can be expensive, and I will basically kind of try to explain why. But specifically for Automotive HMI implementation, so there's a bunch of challenges. First of all, the design and implementation process. I think automotive companies are kind of learning about the correct processes, treating it, I would say, with the care needed, as implementing real-time assets and real-time applications can be quite expensive. There's optimization that can become very expensive. The more you optimize, the more time you're going to spend. The worst case possible is that you implement something and try to optimize it for a while and spend a lot of time and money, and then realizing that what you're trying to do is perhaps not possible. It's out of scope for your target device. So understanding device limitations in advance is very important, and we try to do this as much as we can, working with automotive OEMs, give them consulting before any implementation is done. This is done by evaluating both the target SoC and the concept and requirements. And bets can be used to evaluate the SoC. And I will now show how. But as I said, a lot of these devices have severe performance limitations. And probably the most important of all is embedded devices can overheat really fast. So even if the specs, the device specs mention certain capabilities, when the device actually overheats and there's not a lot of cooling involved, things can go bad very fast. And I will just go forward, rendering UI and HMI. So the complexities I mentioned. The complexities can come from a lot of different things, mainly heavy use of transparency, multi-scene rendering, render layer composition. So you're rendering a lot of different elements that have to blend and transition and layer on top of each other. Transparency is a particular painful subject for real-time graphics. That some solutions exist, but the best solutions are very expensive, and the, let's say, cheaper solutions are not very, they're very limited to specific use cases for sorting, transparency sorting, and alpha blending. And multi-scene rendering, For UI specifically, sometimes you can get along with just rendering a single camera view, a single scene, but more often than not, you cannot. You have multiple UI elements and often with different perspectives. So you might rendering the UI layer, and then you would be rendering some digital twin of the vehicle from a different perspective, or you might be rendering park assist and rendering multiple rear view, top view, different scenes that you have to render in parallel and blend the render textures, the results, scissor them and blend them together. And sometimes you have to apply post-effect image processing shaders on each of these render textures. It can go out of hand really fast, become very, very expensive really fast. And another point is the custom effect shaders, whereas games often use a very, very limited set of standard shaders, surface, unlit, particle shaders, things like this. With UI, in automotive UI, you often have to make very custom shaders for very custom effects. And using a lot of custom effects shaders can cause issues for performance if these shaders are expensive to render. And all of this is amplified by what I mentioned before, these embedded devices overheating really fast, not as capable as desktop hardware, and this can cause a lot of issues when rendering UI. Now we'll move forward. So now talking about specifically these rendering features. So a lot of custom effects UI shaders, I already mentioned this, so I won't go into this again. But this is something that cannot be worked around. A lot of custom effects require custom shaders, and these custom shaders often also use post-processing, stuff like dissipation, accumulation of certain effects, smoke, particles, effects. Often you can use also distance field in 2D to visualize sort of distance warning and all types of glows and highlights. You need a lot of custom effects to be implemented with custom shaders. Another I'd say challenge is usually large amount of texture calls. Often what happens, the teams that actually provide the delivered assets for production, what they often do to cut time and simplify, they extract a lot of textures from the concept material. They say it already exists in the concept, this image, this texture, why not just use it in the implementation? Which kind of leads to overuse of textures, often. Texture calls are slow compared to just arithmetic instructions or simple arithmetic instructions. You want to reduce texture calls. And this in UI specifically, you end up using a lot of textures. Heavy use of transparency and alpha blending. So again, you're layering a lot of UI elements on top of each other, whether it is in an AR application or just an instrument cluster. There's a lot of different elements that layer on top of each other and have to blend seamlessly together in the case of transitions. Fades, dissipations, effects, all types of blending effects and transitions. And since you're dealing with transparency, you cannot just use depth testing, depth sorting. You have to either render things back to front or implement some distance-aided sorting and the like, which often has to be implemented for the specific effect sometimes you're trying to implement. Otherwise, like on the left, you can see often happens things like this where delayering and blending is often wrong as a result. And the solution is usually to render to different render textures and blend the render textures, the layers on top of each other, which is expensive. Dynamic text, a lot of text, a lot of systems and menus. Specifically, we've been working with truck companies as well, which can be scary, the amount of information you have to actually visualize, the amount of systems check, pre-trip, post-trip checks, all type of a lot of text information that has to be rendered and displayed in a lot of different languages for different localizations. So you have to do a lot of text rendering as well. And also curve deformation. You're using a lot of lane data, curve data that you have to deform your augmentations or effects along to highlight lane boundaries, ACC curves, distance warning curves, and the like. You have to do often either basically setting the mesh data every frame along the curve data, or in the vertex shader, accelerate the deformation in the GPU with vertex shaders. And multi-scene and render layer composition. As I mentioned, you're rendering a lot of different layers, often to actually match the detailed concepts that are usually just done in After Effects or some animation tool. The only way to do that is to render to different UI layers and blend them together. More scenes you're rendering, more expensive it's going to be. More render textures, the cost is going to get higher and higher, especially if you have to apply some post-image processing to each of these render layers. There's usually trying to find the minimum viable amount of render textures is usually one of the important things of optimizing for real-time UI. Post-processing image effects, as I mentioned, so you might do some Gaussian or linear blur, you might do some edge detection, anti-aliasing image effects, warping, all kinds of effects can greatly increase the impact on performance. So these were all just examples of rendering features for UI, and the important point is that for bets, we are doing our best to implement workflows that actually utilize all these rendering features that you would find in UI and stress the device accordingly in a realistic workload. Now, some examples of identifying these bottlenecks and optimizing, or how you can use bets to get information for optimization and bottlenecks. Texture compression, GPU texture compression is important for implementing these automotive HMIs. Often these devices are constrained from memory, and GPU texture compression is the way to reduce memory consumption, albeit at increasing GPU calculations to actually decode these compressed textures. So if you're running BETS test or any other rendering workload with texture compression, and all of a sudden the performance increases drastically, you have a memory bottleneck. We can run BETS with different kinds of texture compressions or without, see how different compression formats affect the memory consumption and performance. Also, driver valuation. So OpenGL drivers specifically have a big impact on performance. Different drivers implementation handle memory allocation differently. They offload work from the developers by handling it themselves, but can cause issues, can cause CPU bottlenecks as well. BETS allows you to run with a lot of different graphics APIs, understand the quality of the driver's implementation, how well it performs. You need to understand the different rendering features are only supported in different, in a certain, for example, GLES version 3.2 supports tessellation. If your concept has some very high detailed sort of transition or sort of dissipation effect, something that will require a lot of resolution of the mesh, you would like to use tessellation to do it, but it's only available in 3.2 GLES and above. You need to check the quality of the driver implementation, and if it doesn't exist, you have to descope your concept. You cannot reach that level of resolution of mesh density using tessellation. So that can be used to evaluate your drivers on the target device. Last example, off-screen rendering. This is an important thing for evaluating SoCs. Most of these SoCs have VSync enabled by default. vsync is used to cap the rendering rate to the display refresh rate, which eliminates a screen tearing and also can reduce energy consumption. You don't need to render faster than 60 FPS in most cases, and if you do, you're just wasting energy. But for performance analysis, this is not very useful. You want to know if you're rendering faster than 60. There's a difference between rendering at 100 FPS or 200 for performance analysis. Specifically, your application may render at 60 FPS, but it's very likely that you're going to render multiple applications at once. IVI, the instrument cluster, AR, projection. If your IVI runs at 60 FPS on its own, this is not enough. Once you run all the others in parallel, your performance is going to go down. You need to be able to do proper performance analysis and sort of disregard vsync by doing off-screen rendering. And we have a grid rendering, off-screen rendering solution, which is we basically render to a grid buffer. The grid size can be set by the user. When the grid is filled, we blit to the screen and display the whole grid. But the rendering rate happens the fastest it can render. So you're unlocking the maximum FPS and rendering as fast as you can, which is very important for analysis, performance analysis. Using Unity or Kanzi, it would be a lot harder to profile and evaluate. And BATS allows you to do that. Now going into the actual graphics tests themselves, shortly describing each. As I mentioned, large range of devices, you need a large range of tests to meet your target, what you're trying to implement. Entry level, this is the lowest, in essence, the low-end graphics test, where this is sort of a classic instrument cluster design, analog digital gauges, in essence, with some basic ADAS visualization, sort of on-rail ADAS visualization, turn-by-turn system check information, some custom effects, relatively high amount of textures in context of the target it's going to run on, which is kind of targeted for IMX6, IMX8 sort of devices. High key can handle this fairly okay. Moving to a more complex mid-level. In this case, we're starting to implement more complex 3D effects and lighting, doing a 3D visualization of ADAS on rails, 3D visualization of navigation, while still having the classic gauge elements and information, text, and all these basic things. So this becomes significantly more complex than the simple low-end implementation. And then we have the high-end, the premium instrument cluster, which is a lot more complex. Now you're dealing with 3D visualization, complete sort of 3D ADAS, rendering object detection, distance warning, navigation, points of interest, and on top of it, a classic UI layer to show all your gauges and information. We're now dealing also with more complex lighting, real-time reflections, even particle effects that can be enabled or disabled, and also featuring some digital twin intro to actually deal with now also some PBR shading as well, and more complex realistic rendering on top of classic UI sort of effects rendering. And the IVI test, which can run together with all of these other tests, featuring sort of a digital twin visualization for systems check and the like, 3D navigation visualization, and park assist, both rear view and top view, using also curve-based vertex deformation and such. This is sort of like a mid-level graphic test that can be combined with a lot of those other tests. Another important aspect of that, actually very important, is the parallel test orchestration. So as I mentioned before, we often have to run multiple UI applications at once in parallel. low-end instrument cluster can be run with the IVI and also computer vision test at the same time. As in the car, you would often have the instrument cluster, IVI center console, AR, HUD projection, all these things can often run in the same SoC. So to further profile them, to properly profile them or benchmark the device, you have to run them in parallel. So BATS allows you to do just that. Also using computer vision, you can accelerating computer vision on the GPU will also increase workload on the GPU. You can either run with or without GPU acceleration for computer vision to understand the impact. And once you have run the tests, you can also naturally look at the results, which we offer a whole bunch of metrics, both rendering statistics, what is actually rendering for each frame, but also the performance, which is the most important, is the FPS. And we also, as I mentioned, it's important to view the FPS in context of what is actually rendering. Memory, vertex count, draw calls, and such. Also very important is startup time. Often for these automotive applications, the requirement is that it loads in half a second, less. It has to start the application really fast and start rendering from the moment you start and ignite and start driving. There's no time for loading. And you cannot just put some nifty loading screen and wait a long time. So application startup time is important, and we also provide this as well. And that's kind of in detail about graphics, features of BATS. So as I mentioned, the important thing is to be able to evaluate the SoC, understand the actual limitations of the device, the actual bottlenecks. Hopefully before any implementation has even begun, so you don't waste time in sort of a vicious iteration loop. So as early as possible, you can use BATS to evaluate the device. Also during production, say you already started production, you can still use BATS to understand the performance issues of the device, and also for future implementations. Naturally, this is not going to be your last HMI implementation. It's important that you understand what your device is capable of. If you want to introduce in a modular fashion, also additional applications are being added to run on the same SoC. Before implementing those, BATS offers you a library of sorts of graphics and computer vision tests that are stressing all the common rendering features that you would actually implement in your application later. So before you're starting, you can actually validate or confirm the feasibility of your concepts and requirements. So this is kind of just showing the common approach for HMI development, which is requirements and concepts are being defined, being implemented, profiled, and evaluated on the device. And often performance is not acceptable, so you either modify and optimize your existing implementations, which beginning to iterate takes more time. It may be possible. If it's not, you have to go back to the concept and change the requirements, modify the requirements, and implement again, profile again. Can cause a very time-consuming, and often does end up in a very time-consuming process. So it's important to understand early on if your concept is feasible with actual information on the device. So this kind of shows how to kind of use BATS. So early on you evaluate the concept before approving them and moving to implementation. Only when concept is fully approved and deemed feasible, you begin implementation. And also, hopefully with some implementation plan, what are you going to do? The stages of your implementation. And now I will go to just show you a little demo. So apologies, I'm going to just relocate for a second here and go to the test area where we have all the embedded devices. So I'm going to actually demo how BATS is going to be used. Are we using it in-house? Yes.
And meanwhile, while Damien is setting up the demo, so if anybody has any questions, please write them into the chat and we'll address those after the presentation.
All right, I'm already here and ready. So if there's no questions, I will already be able to show you bets in action. So now you can see this front camera here showing the devices. Oh, and I will also share my screen so I can actually show bets being set up for my own laptop. All right. So hopefully you can see my screen. Sami, can you validate this?
Yes, your screen is full.
All right, then I will continue. So now you're looking at the Orchestrator, which is the tool used to configure, orchestrate the test environment, the test you're going to run, and then launch it either locally or remotely over SSH or ADB. So I'm going to add the graphics test. I'm going to select the mid-level graphics test. There's a bunch of settings, anti-aliasing, rendering resolution, how many times you want to run the test, texture compression. I'm going to use grid rendering, off-screen rendering. Also, anti-aliasing, I'll just keep it as is. Add the test. You can see the test with all these specific configurations. You can also specify the graphics API, in this case using GLES 3.1. And over SSH, I already set the IP to save time. It's important to set where do you want to actually output the results, where do you want to pull them from the remote device. I'm actually going to make a new one quickly. I'm going to call it mid because it's a mid-level test. And I'm going to save to this JSON file the results. And that is all. Hopefully you can see the device over there. It's a bit far, but hopefully you can see that. I clicked. The test has been launched remotely on the device. Does shader compilation, and you can then see how long it took it to actually start. Test is running. In this case, we're using grid rendering, so this screen is only updated when the grid is filled with all the frames. You can probably see that from my camera, not my share. It's going to wait a minute and then look at the results. So the results are done. I'm going to download them. It's going to pull them. Then I can actually show them. At the same time, just for fun, I'm going to just next to it, the NVIDIA Jetson device, I'm going to go to that instead. Just to show parallel test orchestration. But I don't want to, well, I first just want to show the result file I pulled. So let me just pull that. I'm going to skip the Jetson. Don't want to take too much time because we're already running out of time. But you can see the results, all the metrics from the test, how much memory was used, texture memory specifically also, average FPS, startup time. We can see it was a second. And then we can see the results over time per frame. You can see the FPS jumping up and down based on what is actually rendering. Can also make it a bit customizable how we actually show the graph. Can look at other metrics like draw calls maybe also. You can see draw calls fluctuating as well. You can look at the performance and compare it to the what is actually rendering. So this is how we can actually get all the information we want, a list of rendering metrics, and also this list will only grow as we add more and more information. So I'm going to go back to the presentation. This was just briefly bets in action. I want to leave some a bit more time, so I'm going to cut it here, the demo, and move forward. Of course, besides accelerating HMI development and evaluating the device, we can also, actually SoC companies can also use it to evaluate their own SoCs and driver implementations, and can also compare entire platforms. What this means, you can actually, instead of just running on a single SoC, you can run multiple SoCs and spread the workloads accordingly, however you want. Or you can actually compare two SoCs, run the exact same test configuration on two different SoCs, and compare the results running on each of these SoCs. The exact same test, the exact same consistent test. So to summarize, UI and HMI implementations, they have different rendering features comparing to a game workload. UI rendering has its own complexities, and a benchmark that actually evaluates an SoC for automotive UI or HMI should actually utilize the same rendering features. And to properly evaluate the SoC to be used for HMI, automotive HMI specifically, parallel test orchestration is very important, including computer vision, as multiple applications will be running in parallel on the same SoC often. Should evaluate the platform as soon as possible. The sooner you do it, the less time you're going to spend on iterations, which can be very expensive and time-consuming. And only approve the concept and requirements when you know that they are feasible on the target device for the acceptable frame rate. Might be acceptable by requirements to render at 30 FPS, or it might only be at 60 FPS. You need to understand all of this and only approve the requirements when they're deemed feasible. And you can tailor the batch graphics tests and computer vision tests to a lot of different use cases for automotive HMI. You can just run instrument cluster in IVI, different type of complexity. We're going to add additional graphics use cases as well, like AR or navigation specific tests, and add a bunch of different computer vision tests as well. And that is all, pretty much. Can probably move to Q&A. If there's any questions, Sami, back to you.
Thank you, Damien. So if anybody online have any questions, please type into the chat and we'll address those. All right, it looks that there are no questions coming in at the moment. So after the presentation, feel free to reach out to us. We are happy to answer any open questions you guys might have related to the BATs and the benefits of BATs for the automotive HMI development. So thank you all for participating. This concludes the webinar today. Thank you.
Thank you very much.